we can insert now a permanent or static external magnetic field, static homogeneous, but it doesn't have to be homogeneous, but we looked at a homogeneous field, and then you get into an extra term like this. But we also can insert the vector potential of the nuclei magnetic moments, the nuclear spin, and either directly work with this or go through the magnetic field coming from the nuclear spin or the magnetic moments of the nuclear spin. And if we do that, we get two more contributions. Well, in principle we get one, but I'll show you in a second why we get two. So this would be if you just have a magnetic field, be it homogeneous or not, and then with nuclear magnetic moments, we get a Hamiltonian contribution SD, and because that term is called the spin dipolar term, why that is I hope I can show you in a second or two. And that looks a bit complicated. So that's just my factor here, which is sort of the gyromagnetic ratio between the spin angular momentum or spin momentum and the magnetic moment from the spin. And then let's see, divided by 4p. And then we get sum over all electrons, and we have the spin operators of the electrons transposed times position vector and also transposed minus Ri epsilon Ri minus A vector. Now here transposed Ri minus Ra times the spin vector. Transposed divided by the distance to the fifth power, and then times the magnetic moment of the nuclei. So that is called the spin dipolar term or contribution. And it's called spin dipolar because you might remember some electromagnetism. This is actually the normal interaction term between two dipole moments. Now the dipole moments come now here from spin. So you have the magnetic dipole moment coming from the electronic spin, and you have the magnetic dipole moment coming from the nuclear spin. So you have two magnetic dipole moments, and if you look classically at the expression for the interaction between the two, you get this. So this is basically the classical dipole-dipole interaction term between two moments. Now all this part here and the r to the fifth here, if you remember how the vector potential looks like for a magnetic dipole moment, that was something with 1 over r to a third. But now you have to take the curl of that, which means you basically have to take some kind of derivatives of that 1 over r to the third term. And if you take a derivative of a 1 over r to the third term, you're going to get r to the fourth. I mean, it's 1 over r to the third, and if you take the derivative, you get 1 over r to the fourth. Actually, if you look at that r to the third term, it's not really 1 over r to the third, it's just 1 over r squared, because you also have an r vector in the numerator. So So it's from 1 over R2 squared you get to, if you take the derivative, to 1 over R to the third. And that's what we have here, because here we have R squared divided by R to the fifth. So that's essentially 1 over R to the third. So all this terrible looking part here is just comes out of taking this curl here. So it's essentially the magnetic field coming from a dipole moment looks rather complicated. And that's sort of this part in here. Right, now maybe I should make a comment about this transposed here. This is a scalar product. I think Frank uses transposed in his book. You don't necessarily have to do that. I mean, if you sort of transposed makes sense if you consider the vectors always to be column vectors. Then for this here, you better write it as transposed because you need a row vector times a column vector as a scalar product. And for those diamagnetic terms which we had on Tuesday, it's actually very convenient to write it with a transposed. But here it wouldn't really be necessary because this is just a scalar product. And then this is a normal vector, which goes with this one at the end because this stands behind the whole parenthesis, behind the whole quotient. And then this is a scalar product again, and then you have this. So you basically have the scalar product of S and R, and then you have R, the scalar product of R with a magnetic dipole moment of the nucleus. Whereas in this part, you have the scalar product of those two position vectors, and then you have the scalar product of the electronic spin with the nuclear magnetic moment. Now, this is only one term, and I promised you there are going to be two terms. There's a problem with that term. We're talking about electrons with their spin and nuclear magnetic moment, so we're talking about electrons and nuclei. If you remember, try to remember, how does an s orbital look like? You would have to draw the radial function, the radial part of an s orbital, hydrogen 1s orbital. Jack?
It would be an exponential decreasing radial.
Right, exponential decreasing function. So if I come from some distance from the nucleus and get closer to the nucleus, the function rises. And it has a finite value at the position of the nucleus. What does that mean for the probability of the electron to be at the nucleus? Yes?
But there is one.
Yeah, there is one. It's not zero. What do we have here? That's the distance of the electron from a nucleus. And as we just said, if the electron is an s orbital, it has a finite probability being at the nucleus. What happens to that term then? This goes to infinity. So I mean, classically a dipole-dipole interaction is always something if there's a distance between them. Because otherwise, with all that dipole-dipole interaction, you start, if it only makes sense if there's some distance between the two dipoles, at least for the electric ones, which are made by charges. But so this term you can only use, or it describes only correctly, if the electron is not at the nucleus. So one has to do something about that, has in some way to take the limit for the electron, distance between the electron from the nucleus going to zero. And if you do that, you get a second term, which is called the Fermi contact term. HFC, which now looks like, again, this gyromagnetic ratio of the electron. Let me use 0 divided by 4 pi. Then we get some more, 8 pi divided by 3, which comes from taking that limit. And then the sum of all electrons. And then we have a Dirac delta function over the distance of the electrons from the nucleus. And again, like on Tuesday, I mean, you can see I write it all up here, assuming that there's one nucleus with magnetic moment. So if you have a molecule with more than one nucleus with a magnetic moment, of course you have to have a sum over all the nuclei A. But I don't think I had them anywhere, except you make me aware. You mentioned that last week. Okay, so here we have the Dirac delta function, which means that term only contributes if the electron is sitting on the nucleus. It's at the position of the nucleus, because that Dirac delta function, which is which is 0, if that argument is not 0. If there's a distance between them, then it's 0, and it's 1 if the argument of the function is 0. And then we have the electron spin, Si, and again transposed, because it has to be, well, in this notation here, multiplied with the nuclear magnetic moment. So this is essentially, or not essentially, it is the limit of this term for letting the distance go to 0. And both those terms I can write now, and that is partly we also did on Tuesday. I can write them as some kind of operator times, that's going to be a vector, times the magnetic moment of that nucleus.